Welcome, class. This is our fourth lecture on fundamental concepts in chemical engineering, where today we'll be reviewing the critical underlying chemistry of chemical engineering. Here you will learn how to quantify and model reaction rates, so you can determine how fast a chemical process is, how to interpret and manipulate chemical equilibria, so you can predict product yields and shift reactions in your favor using principles such as Le Chatelier's, the role of thermodynamics, including enthalpy, entropy, and Gibbs free energy, in determining whether a reaction is energetically favorable and how much heat will be released or required. You'll also learn about equilibrium constants and how they relate to concentration and partial pressures at equilibrium, giving you insight in how far a reaction will go under specific conditions. Further, you'll learn how to apply ice tables to calculate concentrations of species at equilibrium, using a simple framework to handle complex reaction systems. Finally, you'll learn about the ideal gas law, which helps engineers model gas behavior. Let's start with some basics you may already be familiar with, and that is a mole. A mole is basically a chemist's dozen, but instead of 12, it's a very large number we use to count particles, atoms, molecules, or ions because they're so tiny. So just like we say a dozen of eggs for 12 eggs, we say a mole of atoms, which refers to a fixed number of atoms. And this number is 6.022 multiplied by 10 to the 23rd. This is known as Avogadro's number. It's huge, followed by 23 zeros. It tells us how many particles are in 1 mole of substance. Think of it as a bridge between the microscopic world of atoms and the macroscopic world of grams and liters. Now you might ask, where does this come from? The definition is that Avogadro's number was chosen so that exactly 12 grams of atoms of carbon-12 contains exactly 1 mole of carbon atoms. The mole makes chemistries more manageable. Imagine having to say 602 sextillion particles every time you did a calculation. Instead, we use the mole as a shorthand. It helps us to perform stoichiometry without drowning in zeros. Let's walk through a common example. How many atoms are in 1 mole of sodium chloride, regular table salt? Let's start with the basic. So 1 mole of sodium chloride contains 6.022 times 10 to the 23rd number of molecules. But sodium chloride isn't just a single atom. It's made of 2 atoms, 1 sodium and 1 chloride. So if we multiplied this number by 2, we get the total number of atoms in sodium chloride. So this comes to about 1.204 multiplied by 10 to the 24th in just 1 mole of table salt. Now that we understand what a mole is, let's connect it to something really useful, molar mass. Molar mass is the amount that 1 mole of particle weighs in grams. And by particles, I mean atoms, molecules, or ions, whatever the basic unit of substance is. So just like 1 mole equals 6.022 by 10 to the 23rd particles, molar mass tells you how many grams that enormous number of particles actually weighs. And this is what makes chemistry practical. If you know the molar mass, you can easily convert between the mass and moles using these formulas. You've probably seen this triangle before. Mass goes on top, moles and molar mass go on the bottom. We can rearrange it depending on what we're trying to solve. Let's apply this to a real-world example. How many moles are in 1 gram of water? To do this, we need the molar mass of water. So here we can look at the periodic table. Hydrogen is about 1.008 grams per mole, while oxygen is about 15.999 grams per mole. And since water is H2O, that is 2 hydrogens and 1 oxygen, we calculate this as 2 times 1.008, so 2.016 for hydrogen, plus 1 times 15.999 for oxygen. We add them up and we get a molar mass of 18.016 grams per mole. Now let's use our equation. Moles equals mass divided by the molecular weight. So if we have 1 gram of water, we divide that by 18.016 molar mass. And this gives us a final answer of 0.0555 moles. We can also express that in millimoles, moving the decimal place over 3 places. This tells us that there are about 55.5 millimoles in 1 gram of water. So molar mass is your conversion bridge between mass and moles. It is essential to know before tackling stoichiometry, limiting reactants, or concentration calculations. Let's begin by defining what it means for a chemical species to react. A species is said to have reacted when it's lost its chemical identity, or in other words, when it no longer is the same molecule it was at the start. So how do we define a molecule's identity? It's determined by the kind, number, and configuration of atoms. Change any one of those, and the molecule is no longer the same. There are three main ways a species can lose its identity. First is decomposition. This is when a single compound breaks apart into simpler ones. For example, water decomposing into hydrogen and oxygen gas. The second is combination, or synthesis. Two or more species combine to form a new product. For instance, magnesium and oxygen combining to make magnesium oxide. Finally, we have isomerization. This one is a little different. Here the molecular formula stays the same, but the rearrangement of atoms changes. A good example is glucose converting to fructose. They have the same atoms, but different structure and properties. So even without adding or removing atoms, reconfiguring the positions can also count as a chemical reaction, because the species has lost its original identity. Let's start with a basic reaction example. Suppose we have a species A converting into species B. This is a one-to-one reaction, meaning one molecule of A becomes one molecule of B. We express this reaction rate by defining how fast A disappears and how fast B forms. Since A is being consumed, we give it a negative sign, negative RA. Since B is produced, we write this as RB. In this one-to-one example, the rate of disappearance of A is equal to the rate of appearance of B. Let's define these more formally. The rate of disappearance of reactant A is given by the change in concentration over time, negative dA, or over dt. For products like B, the rate is positive. It's just the rate of concentration increase, so dB over dt. Note here also that reaction rates are expressed in units of molarity per second, or rather moles per liter per second. This tells us how fast the concentration of a substance is changing. We can plot this as such. The blue line represents the change in molar concentration of A, the reactant, which is decreasing over time, while the red line is the concentration of B, the product, which is increasing with time. Notice how slopes are steepest at the beginning. That's when the reaction is fastest. As time goes on, the rate slows down as concentration levels off, and the system approaches equilibrium. If we actually want to measure this in real life, there is a few different ways we can do this. The first way is spectroscopy, where we can track useful reactants or products through which are colored or have specific wavelengths or absorbance. Pressure sensors, which can detect gas production. Titration, which is a classic method for measuring acid-base reactions. And calorimetry, which allows us to track the temperature changes from heat released or absorbed during the reaction. So far, we've defined how to express and measure reaction rates. Let's now look at how rates depend on the concentration of reactions and how we can determine a reaction's order using real data. Let's connect stoichiometry, the ratios in chemical equations, with reaction rates. Stoichiometry doesn't just tell us how much product we get from a reaction, it tells us how fast each species is going to be consumed or produced, relative to the others. In a chemical equation, where A moles of A reacts with B moles of B to form C moles of C and D moles of D, the rate at which each species changes is related to its stoichiometry coefficient. The rate of disappearance of A divided by A is equal to the rate of disappearance of B divided by B is also equal to the rate of formation of C divided by C and the rate of formation of D divided by D. This ensures that all the rates are normalized to reflect the stoichiometry of this reaction, so we compare how quickly each species is used up or formed relative to the others. The negative signs are for the reactants because they are consumed. The products are forming, so their rates are positive. Let's try a simple example, 2A to B. This tells us 2 units of A are consumed to make 1 unit of B. From this, we write minus RA divided by 2 is equal to RB divided by 1, which rearranges to negative RA is equal to 2RB. This tells us that A disappears twice as fast as B appears. Here's another example where A plus 2B goes to C. If we're told the rate of A disappearing is 10 moles per meters cubed seconds, then the rate of B disappearing is 20 moles divided by a meter cubed seconds, because it's used up twice as fast. Let's now apply this to a real industrial case, ammonia production, where we have N2 plus 3H2 goes to 2NH3. Let's say you're measuring hydrogen consumption in moles per second. Using stoichiometry, we can calculate how much ammonia forms and how much nitrogen is needed per second. We write this as the negative R hydrogen divided by 3 is equal to the negative R nitrogen divided by 1, which equals R of ammonia divided by 2. This shows the relationship between all three rates. Now that we've seen how to relate the rates of different species using stoichiometry, let's talk about what actually controls how fast a reaction goes. There are four main levers we can pull: concentration, temperature, catalysis, and physical conditions such as surface area and pressure. Let's start with concentration. This one's pretty intuitive. The more reactants you have, the more collisions per second you're probably going to get. And that generally means a faster reaction rate. Temperature, on the other hand, speeds things up, giving molecules more kinetic energy to overcome activation barriers. We'll get more into this later when we cover the Arrhenius equation. Catalysts don't affect the stoichiometry, but they do change the path that reaction rates take, usually lowering the activation energy required. Finally, in a gas phase or heterogeneous system, increasing the surface area or pressure helps molecules to find each other faster. Let's go a bit deeper on concentration, since this is where we're heading next with the rate laws. Look here on the left-hand side. This is a dilute system with just a few molecules. A and B don't find each other very often, so reaction is slow. Here on the right, on the other hand, we compare it to a concentrated system. It's more crowded, so there is more molecules per volume to collide, and thus a faster reaction will occur. So even before we get into math, we can already visually see why concentration has a big effect on reaction speed. But how fast? That's where rate laws come in. Some reactions double in rate when you double the concentration, others quadruple. Some don't change at all. Let's now look at reaction order, which gives us a mathematical relationship between the concentration and the reaction rate. Let's start with zero order reactions. In these reactions, the rate is given completely independent of concentration. That means even if you increase the amount of reactant, the reaction won't speed up. This usually happens when the reaction is limited by something else, like a saturated catalyst surface, where all the reactive sites are full. Here we write the law as negative Ra is equal to K, a rate constant. A good example of this is the decomposition of ammonia on a platinum surface, where ammonia is converted into nitrogen and hydrogen. In this case, the negative R of ammonia is equal to K because once the catalyst is saturated, the reaction proceeds at a constant rate. As you can see here in this graph, this is reflected as a linear drop in concentration over time. The rate versus concentration graph is just a flat line, so no change in rate as concentration increases. Let's now look at a first order reaction. In these, the rate does depend on the concentration. Specifically, it's directly proportional to how much reactant is present. If we look here at negative Ra is equal to K multiplied by the concentration of A. This means if you double the concentration of A, the reaction rate also doubles. A good example of this is the decomposition of dinitrogen pentoxide. Here, dinitrogen pentoxide is converted into nitrogen dioxide and oxygen. So we get the negative R of dinitrogen pentoxide is equal to the rate constant multiplied by the concentration of dinitrogen pentoxide. The concentration, therefore, decreases exponentially over time, as you can see here, with the curve getting shallower. The rate increases linearly with concentration, as shown in the bottom plot. Let's now look at a second order reaction. These are a little bit more sensitive to concentration. Here there are two common forms. Negative Ra is equal to the rate constant multiplied by the concentration of A squared when the reaction depends on two molecules of A, or it's equal to negative Ra is equal to the rate constant of the concentration of A times by the concentration of B when it involves two different reactants. In this example reaction, hydrogen plus iodine goes to hydrogen iodide. The reaction rate depends on both hydrogen and iodine concentrations. Thus, negative R of hydrogen is equal to the rate constant multiplied by the concentration of hydrogen multiplied by the concentration of iodine. You can see the concentration decreases even more gradually here, and the rate increases non-linearly. The curves get steeper as concentration rises because the rate is proportional to the concentration of X squared, or the concentration of the reactant squared. Just a quick note here also. We often write concentration as C of A, but this is equivalent to writing the reactant in a square bracket, which denotes the molar concentration of that reagent. So the square bracket of X is equal to Cx. This is a common stylistic difference between general chemistry and chemical engineering, but please be aware that both are somewhat interchangeable. In summary, let's look at these graphs again. Make a mental note that zero order is a linear concentration drop and a flat rate. First order is an exponential decay and a linear increase in rate. And second order is an even slower decay and an exponentially increasing rate rise. These figures help you instantly identify reaction order when analyzing experimental data. So now we know how concentration affects the rate through reaction order, but that's only part of the picture. The major factor that controls the rate is temperature. To understand this, we turn to the Arrhenius equation, which tells us how temperature and activation energy affect how fast a reaction happens. So let's look at how temperature affects how fast a reaction goes, specifically how it affects the rate constant. This is where we use the Arrhenius equation. The basic form of this Arrhenius equation is K is equal to A multiplied by the exponential of E of A, or activation energy, divided by RT. This tells us that the rate constant depends on the activation energy and the temperature. Let's break this down. So K is the rate constant, which tells us how fast the reaction happens. A is a frequency factor, how often collisions happen with proper orientation. So E is the activation energy, an energy barrier that reactants must overcome before a reaction happens. R is the gas constant, 8.314 joules per mole Kelvin, and T is the temperature in Kelvin. Here's something useful to remember. Even a small temperature increase, say from 300 Kelvin to 310 Kelvin, this can often double the rate constant for many reactions. That's how sensitive K is to temperature. Taking the natural log of both sides gives us the natural log of K is equal to the negative activation energy divided by RT plus the natural log of A. We can rearrange this into the slope-intercept form, or rather, y equals mx plus c, where y is the natural log of K, x is 1 over t, m, the slope, is the negative activation energy over R, and c is the natural log of A. On the graph, we plot the natural log of K on the y-axis and 1 over t on the x-axis, and you'll get a straight line. The slope of this line is the negative activation energy over R, and the y-intercept is the natural log of A. This lets us extract activation energy directly from experimental data. So now that we've seen how to graph this, what if you only have 2 points, 2 rate constants at 2 temperatures? Let's go to the next slide now and see how we use a simplified 2-point form to calculate the activation energy without needing a graph. Since sometimes we don't have a full set of data for graphing, sometimes we want to use an estimate for activation energy using just 2 rate constants at 2 different temperatures. In those cases, we use the 2-point version of the Arrhenius equation. Let's start with the linearized form of the Arrhenius equation we just saw, this time making it for the temperature 1 and rate constant of that temperature K1. But we can also do that for the other temperature and rate constant, T2 and K2. Subtracting these 2 equations from each other allows us to eliminate the natural log of A, since although it's a constant, it's not typically known. So we take the log of K1 minus the log of K2 is equal to the difference of the 2 right-hand sides, simply by just subtracting these 2 different equations. We're left with the natural log of K1 over K2 is equal to the negative activation energy over R multiplied by 1 over T1 minus 1 over T2. This gives us a compact equation that relates 2 known rate constants to the activation energy. And finally, we can solve for activation energy, where activation energy equals R multiplied by the natural log of K1 over K2, all divided by 1 over T1 minus 1 over T2. This allows us for a more immediate calculation of the activation energy, and is especially useful in lab or industrial settings when we only have 2 temperature rate data points. Let's now work through an example, plugging in natural values to calculate the activation energy for a real reaction. Let's apply this 2-point version of the Arrhenius equation to this example. Here we're given 2 rate constants for a second-order reaction at 2 different temperatures. So K1 is equal to 5 multiplied by 10 to the negative 6 at 560 Kelvin, and K2 is 1.2 multiplied by 10 to the 4 at 610 Kelvin. We'll use this form of activation energy is equal to R multiplied by the natural log of K1 over K2, all divided by 1 over T1 minus 1 over T2. Substitute the known values into the equation, and make sure you match the rate constants to the correct temperature, and always use Kelvin for temperature. R is the rate constant, 8.31 joules over moles Kelvin, and we're using the natural log of the K ratio. Solving an equation gives us an activation energy of about 65,000 joules per mole, or rather 65 kilojoules per mole. As a quick reminder, always convert temperature to Kelvin. Quite often, temperature is given in Celsius and will need to be converted using this equation here. Let's talk about how temperature affects reaction rate. As a rule of thumb, high temperatures generally speed up reactions. This is because increasing temperature boosts molecular kinetic energy, which means more collisions have enough energy to overcome the activation barrier, EA. This is captured mathematically by the Arrhenius equation, where K is equal to A multiplied by the exponential of negative activation energy divided by RT. This shows that K, the rate constant, depends both on activation energy and the temperature. As temperature increases, this exponent becomes less negative, so K increases. Here's a helpful summary. So increasing temperature leads to increasing the rate constant, and decreasing the activation energy also leads to increasing the rate constant. As you can see from this plot, this is not a linear relationship. It's exponential. Thus, a small increase in temperature can cause a large increase in K. As mentioned, a general rule of thumb is for every 10 Kelvin increase, the rate roughly doubles. It's an approximation, but it does illustrate just how sensitive the rate is to the temperature. So let's recap. Higher activation energy equals slower reaction, and a higher temperature equals faster reaction. Let's look at a real-world example, the Haber process, where ammonia is synthesized at 400 to 500 degrees Celsius in order to achieve a fast enough reaction. It's worth bearing in mind that this comes with some caveats. Increasing the temperature can also increase the side reactions or undesired reactions. In these cases, it may be more favorable to use a catalyst instead of increasing the temperature. Let's now look more closely at activation energy, or EA. EA is the minimum amount of energy a reactant molecule must have to form the transition state, the unstable high-energy arrangement that bridges the reactants and products. Only molecules with enough kinetic energy, energy equal to or greater than the activation energy, and the correct orientation will actually go on to form the products. In this left diagram, you can see a kind of energy hill. Reactants must climb all the way to the top of this hill to get over to the product side. So even if you add energy, if it's not enough, it will remain at the reactant side. You must reach what's called the transition state at the top of this energy mountain. This is what determines the rate of the reaction, not whether it's thermodynamically favorable, but how quickly it happens. Let's take methane combustion as an example. Even though the reaction is highly exothermic, it doesn't start on its own. You still need a spark to overcome the activation barrier and initiate the process. That spark supplies the initial energy needed to get some molecules over that barrier, and from there, the reaction becomes self-sustaining. Now, if we want to make the reaction faster, we need to lower the activation energy hill, and that's where catalysts can come in. Catalysts give molecules an alternative path and a lower activation barrier. That's shown clearly in the right-hand diagram. The green curve represents a catalyzed reaction with a lower activation energy. The molecules can move over the hill and react more readily. So activation energy controls how fast a reaction occurs. That's kinetics. But what about how far a reaction goes, whether it goes spontaneous or favors products or reactants? That's where thermodynamics comes in. And we'll make that distinction next. Now let's link activation energy with enthalpy change, delta H, using energy diagrams. We've seen that the activation energy, EA, tells us about the rate of a reaction. It's the barrier the reactants must overcome. But the delta H tells us the net change in energy between where the reaction starts and where it ends. That's a thermodynamic quantity. You can think of enthalpy as the total heat content of a system. It reflects how much energy is stored in the bonds of the molecules. So when we say a reaction is exothermic, aka delta H is less than 0, it means energy is released. The products have less stored energy than the reactants. When it's endothermic, so delta H is greater than 0, the system absorbs energy. The products end up with more stored energy. In the exothermic reaction on the left, the products are lower in energy than the reactants. Energy is therefore released, so delta H is negative. In contrast, in the endothermic reaction on the right, the products are higher in energy than the reactants. Energy is thus absorbed, so delta H is positive. Let's walk through some equations we can derive from this energy plot. The forward activation is the energy from the reactants up to the transition state. Thus, we can write that the activation energy going forward is equal to the transition state, or the activated complex, minus the reactant energy. While the reverse activation energy is from the products back to the transition state, so this is given as the reverse activation energy is equal to the transition state energy minus the product energy. So delta H is thus the energy difference between products and reactants, and can be given as products energy minus the reactant energy. It's also important to realize that delta H is also equal to the forward activation energy minus the reverse activation energy. So by combining the activation energy in both directions, you can also estimate the enthalpy change of the overall process. This connection shows how thermodynamic favorability, delta H, and kinetic accessibility, activation energy, are related but not necessarily the same. A reaction can be thermodynamically favored, but still very slow if activation energy is high. Now that we've seen how delta H fits into energy diagrams, let's go a little bit deeper in the thermodynamics and see how enthalpy relates to spontaneity, entropy, and free energy. So here's the Gibbs free energy equation. It tells us whether a reaction is thermodynamically favorable or not. We'll use this to connect heat, disorder, and temperature into one prediction of whether a reaction wants to happen. We define free energy as the combination of three things: enthalpy, delta H, entropy, delta S, and the temperature, where delta G is equal to delta H minus temperature times delta S. This is the central equation of chemical thermodynamics. Let's break it down. We'll start with the delta H, enthalpy. Enthalpy is the heat transferred at a constant pressure. Chemically, it reflects the energy stored in chemical bonds and comes from difference between bond breaking and bond forming. If more energy is released in forming bonds than was used to break old bonds, then delta H is negative, as we've just seen. The reaction gives off heat, and we call this exothermic. If you need to put energy in to make a reaction happen, delta H is positive, and it's endothermic. For example, methane combustion is extremely exothermic. Thus, it releases a lot of heat, and delta H is negative 962 kilojoules per mole, which is very favorable. Let's now talk about entropy. Entropy measures the number of microstates, how many ways particles can arrange themselves. It reflects how dispersed or spread out the system becomes. Imagine a reaction breaks one molecule into multiple. The reverse would require all those different particles to come back together in exactly the right place to reform the original molecule. This is both statistically less likely and thus thermodynamically uphill. Entropy thus favors the direction where the system becomes more spread out, not because it's messy is better, but because there is far more ways for a system to be disordered than it can be in ordered states. Like perfume spreading throughout a room, or a paper being shredded, the reverse is not necessarily impossible, but it's statistically less likely to happen. Thus, when delta S is positive, the system is more disordered, like when a liquid becomes a gas, one molecule breaks into several. When delta S is negative, the system becomes more ordered, fewer particles, less freedom. That's where temperature plays a role also. Temperature determines how much weight entropy has in that delta G balance. That's why it's T times delta S appears in the equation. Entropy only helps a reaction if it's high enough in magnitude to overcome the enthalpy costs. Take, for example, the decomposition of calcium carbonate into calcium oxide and carbon dioxide, which increases in entropy going from one solid to a solid plus a gas. So delta S is positive, and the reaction becomes more favorable at higher temperatures. In conclusion, both delta S and delta H contribute to the delta G, the Gibbs free energy, but temperature decides how much entropy really matters. Let's now apply this to a different combination of enthalpy and entropies. Unpacking each term, let's look at how they interact with four common thermodynamic scenarios. So let's bring back the Gibbs free energy equation, where delta G is equal to enthalpy minus T times delta S. This time to focus on delta G itself, and what it really tells us about spontaneity. So the Gibbs free energy, delta G, tells us whether a reaction is spontaneous under constant pressure and temperature. A negative delta G means the process is thermodynamically favorable. It wants to happen. A positive delta G means it's non-spontaneous. Let's go a little bit deeper. If delta H is negative and delta S is positive, heat is released and disorder increases. The reaction is always favorable. Think combustion reactions. But when delta H and delta S are in opposition, like both negative or both positive, the temperature becomes the deciding factor. If entropy is working against you, high temperatures will make delta G less favorable. If entropy is working for you, high T helps. This table summarizes the four main scenarios. This helps us understand why some reactions require heat and others proceed spontaneously at room temperature. Let's talk about chemical equilibrium, a central concept in reaction engineering. This occurs in reversible reactions, which means the products don't just stop reacting, they can actually turn back into reactants. Here's a generic reversible reaction. A plus B can turn into C plus D. But C and D can also react to form A and B. At equilibrium, the rate for the forward reaction, RF, is equal to the rate of the reverse reaction, RR. Importantly, equilibrium is dynamic, not static. Even though we can't see changes in concentration, reactions are still happening, just at equal rates. So the concentration of reactants and products remains constant over time, but they're not necessarily equal in value. That's a common misconception. Let's look at a classic example. Nitrogen plus 3 hydrogens reversibly forms 2 ammonia. This is the Haber process, one of the most important industrial reactions. We use this to make ammonia, the key precursor for fertilizer. Let's now look at this graph of concentration over time. Nitrogen and hydrogen decrease as they're consumed, while ammonia increases. Eventually, all three flatten out. That's when equilibrium is reached. In engineering, our goal is almost always to shift equilibrium towards the products we want, which we'll also look into in this lecture. Let's now talk about equilibrium constants. These give us a way to quantify how far a reaction proceeds before it levels off. We start with a general balanced chemical equation, where AA plus BB forms CC plus DD, where lowercase letters are their stoichiometric coefficients. The equilibrium constant Kc is calculated by the concentration of the species. So Kc is equal to the concentration of C to the power of C multiplied by the concentration of D to the power of D, divided by the concentration of A to the power of A multiplied by the concentration of B to the power of B. This is the ratio of products over reactants, each raised to their respective powers. For gaseous reactions, we often use Kp instead of Kc, where Kp is equal to Kc multiplied by RT to the power of delta N, where delta N is the change in moles of gas, moles of the products minus moles of reactants. K measures the extent of a reaction. This is how far it goes towards forming products before equilibrium was reached. A larger K means reaction favors products. A smaller K means reaction favors reactants. Here is an example. The equilibrium between dinitrogen tetraoxide and nitrogen dioxide. Here, Kc is equal to 0.4. The value is less than 1. So at equilibrium, more N2O4 remains than NO2 is formed. We say this reaction lies to the left, favoring reactants. Temperature can also affect the equilibrium constants. For exothermic reactions, decreasing the temperature increases K. It favors product formation, whereas endothermic reactions, increasing temperature increases K, again favoring products. Let's now talk about the reaction quotient, Q, a tool to help us predict if a reaction will shift to the left or the right to reach equilibrium. Let's start with a generally balanced equation, where AA plus BB is reversibly reacting to CC plus DD. Just like equilibrium constants, we set up a ratio of products to reactant concentrations raised to the stoichiometric coefficients. But here the key difference is QC uses the current concentrations, even if the reaction hasn't yet reached equilibrium. Kc uses concentrations only at equilibrium. This means that QC acts like a snapshot. It tells us where the system is right now and whether it needs to shift to reach equilibrium. This table summarizes the comparison. If QC is less than Kc, there are too many reactants, so the system shifts to the right towards product. If QC is greater than Kc, there are too many reactants, so the system shifts left towards the reactants. If QC equals Kc, we're already at equilibrium. No net shift occurs. Let's again look at this example, where N2O4 is reversibly forming NO2. We're told that the Kc is equal to 5.85 multiplied by 10 to the negative 3. And the measured concentrations are 0.0225 molar of nitrogen dioxide and 0.331 molar of nitrogen tetraoxide. Plugging these values into the QC expression, we find that QC is equal to 0.0255 squared divided by 0.0331. which comes to 0.0197. Comparing that to the Kc, we see that Qc is greater than Kc. Since there are too many products relative to equilibrium, the reaction will shift to the left, favoring the formation of reactants to restore the balance. Let's now look at one of the most powerful tools for solving equilibrium problems, the ice table. This stands for initial, change, and equilibrium. We use this method to calculate unknown equilibrium concentrations based on stoichiometry and a known equilibrium value. Let's walk through one to demonstrate how they're performed looking at the decomposition of NOBr into NO and bromine. Let's now fill in our ice table. Initially, we have 0.64 molar of NOBr and 0 for the products. During the reaction, we lose 2x of NOBr because of the 2 to 2 to 1 stoichiometry, and we gain 2 of NO and 1 of Br. So we can write this in as minus 2x plus 2x and plus x. We're told that NOBr is at equilibrium 0.46 molar. So we can use 0.64 minus 2x is equal to 0.46. Solving for x, we get that x is equal to 0.09. This lets us calculate the equilibrium constants of the other products now. So NO is 2x equals 0.18 molar, and bromine is x, so 0.09 molar. Now let's plug everything into the equilibrium expression. Remember, for the Kc equation, it's always products over reactants, and each term is raised to the power of a stoichiometric coefficient from the balanced equation. In this case, we have Kc is equal to the concentration of NO squared multiplied by the concentration of bromine divided by the concentration of NOBr squared. Notice how both NO and OBr are squared. That's because each has a stoichiometric coefficient of 2 in the balanced chemical equation. That means 2 moles of each are involved, so their concentrations are raised to the power of 2. Bromine has a coefficient of 1, so it just stays as it is. Adding in these values and solving gives us a Kc of 0.0138. This is how we use the ice tables to calculate the Kc as well as the equilibrium concentrations of a reactant. Now let's step up a level and work through a problem where we're not given the equilibrium concentration. Instead, we'll have to solve for it. Looking at the reaction of hydrogen and iodine to form HI at 448 degrees Celsius, we start with 0.65 molar of hydrogen and 0.88 molar of iodine with no HI. The Kc is given as 50.5. So let's set up the ice table. So we know hydrogen and iodine each decrease by x, while HI increases by 2x. Let's set up the ice table. So we know the concentration of hydrogen is 0.65, and we know that the concentration of iodine is 0.88, and the concentration of reactant is 0. Based on the stoichiometrics of the equation, hydrogen and iodine both decrease by x, while hydrogen iodide increases by 2, giving us 2x. This thus gives us an equilibrium of 0.65x for hydrogen, 0.88 minus x for iodine, and 0 minus 2x for HI. Let's now plug these into the equilibrium expression. So this will give us 2x squared over 0.65 minus x multiplied by 0.88 minus x. This expands to 4x squared over 0.65 minus x multiplied by 0.88 minus x. And we can put this as equal to the equilibrium constant, 50.5. Solving for this, we develop a quadratic equation, and we can use the quadratic formula to solve for x. And this gives us 2 solutions. One solution is not valid, as plugging this back into the equation will give us a negative concentration. The second value given does make sense, and therefore this must be the correct value. So this is 0.567. Putting this value back into the equations, we get that the hydrogen concentration at equilibrium is going to be 0.083. The iodine concentration at equilibrium is going to be 0.313, and that the hydrogen iodide concentration is going to be 1.134. This is the kind of ice table where you work backwards from Kc, and solving it requires algebra and quadratic solving. Just make a note also that in these examples, we've only used the initial reactant concentration at time 0, that is, before a reaction has started. However, in theory, ice tables can be applied at any point during the reaction before equilibrium is reached. If you're instead given a non-zero amount of the product at the start, simply enter the value in the initial row and follow the same procedure. The logic of the ice table remains the same, only the starting point will change. This brings us to Le Chatelier's principle, which states that if a system at equilibrium is disturbed, it will shift into the direction that counteracts the disturbance to restore equilibrium. Let's start with the general reversible reaction. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, and the concentration of reactants and products remain constant, but only as long as the system remains undisturbed. Le Chatelier's principle tells us that if a system at equilibrium is disturbed, it will shift in the direction that counteracts the disturbance. This is a system's way of trying to restore balance, kind of like a chemical tug of war that pulls back towards equilibrium. Here's a summary table to preview how different changes affect equilibrium. Here's a table summarizing the different perturbations of the equilibrium. Moving forward, however, we're going to dive more deep into how pressure, temperature, and concentration affects equilibrium. Let's first take a look at concentration and understand how it affects the chemical equilibrium balance. Changing the concentration does not affect the value of the equilibrium constant K, but it does disturb the ratio of products and reactants, which is what we call Q, the reaction quotient. When you change the concentration of a reactant or product, you push the system away from equilibrium. This makes Q not equal to K, and the system will shift to bring Q back to K. This is Le Chatelier's principle in action. Let's look at a familiar example from a few slides back of hydrogen reacting with iodine. We're told the system was already at equilibrium, but what happens if we add extra hydrogen? That means we've disturbed the system, and it needs to shift to re-establish a new equilibrium. Let's use the ice table to predict the new concentrations. Here I will enter the equilibrium concentrations from a few slides back. However, I will now change the initial concentration of hydrogen to 0.3. Let's now recalculate from this new starting point. Thus, the new equilibrium will be 0.3 minus x, 0.313 minus x, and 1.134 plus 2x. We can plug these values back into the Kc equation and solve. Here we use a quadratic formula again and assess the results for feasibility. One of the results is clearly not valid as it results in negative concentrations. So this means that x must equal 0.115. Plugging these back in, we get new equilibrium concentrations of 0.185, 0.198, and 1.364. So by adding hydrogen, the system is again shifted to the right, towards the products, increasing hydrogen iodide, and consuming both hydrogen and iodine, just like Le Chatelier's principle had suggested. Let's now apply Le Chatelier's principle to pressure changes. We know that if a system at equilibrium is disturbed, it will shift to oppose the change and restore equilibrium. In the case of gases, we use what's called the ideal gas law, PV equals nRT, which relates pressure, volume, temperature, and the number of moles of gas, where P is the pressure in atmosphere, V is the volume in liters, N is the number of moles of gas, R is the gas constant, and T is the temperature in Kelvin. Now imagine we decrease the volume of a gas phase system. According to PV equals nRT, pressure must go up. This increase in pressure is a disturbance, and the system wants to reduce it. Now imagine we decrease the volume of a gas phase system. According to PV equals nRT, pressure must go up. The increase in pressure is a disturbance, and the system wants to reduce it. To reduce the pressure, the system shifts to reduce N, the number of gas molecules, because fewer gas molecules means lower pressure. The classic example of this is the synthesis of ammonia, where nitrogen plus 3 hydrogens goes to 2 ammonias. Thus, we go from 4 molecules of gas on the left to 2 molecules of gas on the right. So if pressure increases, the system shifts to the right, toward fewer gas molecules. You can remember this as an increase in P leads to a decrease in V, which favors the side with the fewest number of moles. This visual demonstrates the idea here. If we compress the system, it shifts to reduce the gas particle count. Also, from basic definitions, concentration is simply moles per volume. So the concentration of A is equal to N over V. We can rearrange this into PV equal nRT to isolate for pressure, and we get the concentration of A is equal to the pressure of A divided by RT. So this directly relates pressure changes to the concentration, which ties into Q and affects equilibrium shifts. But this does not change the equilibrium constant K. Let's now explore temperature, the only factor that changes the equilibrium constant K. We start with this important equation. Delta G is equal to minus RT multiplied by the natural log of K, which can be arranged as the natural log of K is equal to the negative of delta G over RT. This equation directly links Gibbs free energy change to the reaction rate equilibrium constant K. And it's good to remember that delta G itself also comes from delta G is equal to delta H minus T delta S. So we can actually substitute that in and get the natural log of K is equal to 1 over T multiplied by delta H over R plus delta S over R, which is known as the Van Hoff equation. And it shows us that K is dependent on temperature, and not just temperature alone, but on enthalpy and entropy too. What does this mean for equilibrium? Well, firstly, K very much depends on temperature through both enthalpy and entropy. And for exothermic reactions, where delta H is less than 0, as temperature increases, K gets smaller, and equilibrium shifts towards the reactants. Since one can think of delta H as representing whether a reaction releases heat, exothermic, or absorbs heat, endothermic, if a reaction is exothermic, aka delta H is less than 0, it has already given off heat. If you then raise the temperature, it's like dumping more heat into the system, and according to Le Chatelier's principle, the system wants to counteract that, so it will shift back towards the reactants to soak up that extra energy. That means K decreases at higher temperatures, less product is favored. On the other hand, if a product is exothermic, i.e. delta H is greater than 0, it needs heat to proceed. It's heat hungry, so if you increase the temperature, you're giving the system what it wants, aka more energy, and the system shifts towards the right, aka the products, and K increases. This Van Hoff graph shows the relationship clearly, where the y-axis is the natural log of K, and the x-axis is 1 over T. The slope of this line is the negative delta H over R, so for exothermic reactions, delta H is less than 0, and the slope is positive, meaning the natural log of K decreases as temperature increases. For endothermic reactions, the slope is negative, meaning that the natural log of K increases as T increases. So this graph gives us a visual of how K responds to temperature based on its sign, delta H. In summary, temperature is the only case where the actual value of the equilibrium constant changes. Concentration or pressure may temporarily shift the system, but the equilibrium constant doesn't change. Temperature, however, changes the entire energy balance, and K adjusts accordingly. Let's talk about how reaction rates relate to the equilibrium. Remember, kinetics is about how fast reactions go, while equilibrium tells us how far they go. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So we can put the forward rate and the reverse rate as equal to each other. Rearranging and putting the forward rate constant over the reverse rate constant, we get to this equation here. We see this simplifies to as equaling the equilibrium constant. This shows us how the equilibrium constant is thus related to the ratio of the forward and reverse constants. Let's now make the connection to thermodynamics. Using the equation of the natural log of K is equal to the negative of delta G over RT, or rather, K is equal to the exponential of negative delta G over RT. In each case, we see that the ratio of these rates is given by the free energy differences. Thus, if delta G is negative, K is greater than 1, meaning the forward rate constant is greater than the reverse one, and the forward reaction is favored. If delta G is positive, then K is less than 1, meaning the reverse reaction dominates. That's a reactant-favored equilibrium. Let's now look at catalysts and what they do. Catalysts lower the activation energy barrier for both the forward and the reverse reactions. They provide an alternative pathway with a lower energy hill to climb. But here's the key. Catalysts do not change the delta H of the reaction. The energy difference between the reactants and the product stays the same. Let's now talk about catalysts and what do they do. Catalyst lowers the activation barrier for both the forward and the reverse reactions. They provide an alternative pathway to lower the activation energy hill. But here's the key. They do not change the delta H of the reaction. The energy difference between the reactants and the product stays the same. That means both the forward rate constant and the reverse rate constant increase equally. Both reactions speed up. So if both rates increase proportionally, the ratio, given by K is equal to the forward rate constant over the reverse rate constant, stays the same. K is unchanged. The equilibrium position doesn't shift, only the speed at which equilibrium is reached changes. That's why we say catalysts increase the rate of reaching equilibrium, but they do not actually change the equilibrium itself. This brings us to the end of the lecture. By now you should be able to describe reaction rates and how they depend on reactant concentrations. Connect thermodynamic concepts like enthalpy, entropy, and free energy, and how they determine whether a reaction is energetically favorable. You should now be able to analyze chemical equilibrium using equilibrium constants such as K, reaction quotients, and ice tables to predict how far reactions proceed and in which direction they proceed. You should be able to explain how activation energy and temperature affects the rate constants using, for example, the Arrhenius equation. And finally, you should be able to apply the ideal gas law, PV equals nRT, especially to be able to understand how pressure and volume influences a reaction's equilibrium.